Um, Good evening, everyone. So today I'm going to take you through our work, graph reasoning, computational modeling for conception probability estimation using heterogeneous data. So our keywords, we have conception probability prediction, knowledge graph reasoning, fertility and reproductive health, survival and causal modeling, heterogeneous biomedical data, and computational fertility. So traditional fertility tools like calendar and ovulation kits lack personalization and accuracy. They don't fully capture the complexity of hormonal, lifestyle, and temporal factors. So with the rise of digital health and machine learning, we now have the opportunity to build more dynamic data-driven models. Our project aims to fill this gap by integrating multiple data types and modeling conception probability per cycle. So the keywords in context, we have cycle indexed survival modeling, mechanistic features, a knowledge graph, graph embedding. These ones have latent representations of the node, time series transformer. These ones capture cycle-wise temporal dynamics. Light GBM, this one, it is interpretable, baseline for survival modeling, late fusion, causal inference, for formal prediction. So to ground our work, we reviewed several papers. So this table summarizes models like CNN, RNN, random forest, and graph-based architectures like GCN and RGCN. We noted their strengths like high accuracy and relational modeling, but also their limitations such as lack of temporal awareness and poor interpretability. So this gap helps us to shape our modeling choices. The domain challenge is so clear. Traditional fertility tools don't reflect the complexity of real-world conception. Computationally, we face the task of integrating diverse data types, mechanistic features, cycle sequences, and graph relationships into a unified model that's both accurate and interpretable. So the domain problem here is we need actionable cycle level predictions for patients and clinicians. And then the computational problem, we have a modeling, how to model a multimodal cycle indexed and a graph structured data for conception prediction across diverse patients. So next, our objectives focus on building a robust, interpretable AI system that integrates diverse data, sources, and research questions that guide our exploration into feature importance, model architecture, causal inference, and fairness, ensuring that our work is both technically rigorous and clinically meaningful. So next, our contributions, graph temporal causal pipeline, with the fusion of embeddings plus the transformer plus the T-learner and fairness audits give us a deployment ready system. And then our outputs, we have a validated model with a custom knowledge graph of 300 with 3,244 nodes. And then our AI model is called Conceive Score. And then with the sharp visualizations, open source notebooks. So next, our system architecture begins with raw tabular and cycle index data. We engineer mechanistic features and construct a heterogeneous knowledge graph. So this graph feeds into the RGCN and GAT models to generate relational embedding. So we also apply a transformer to model temporal dynamics. So these outputs are fused either via late averaging or stacked meta-learners and passed into the causal inference layer for treatment effect estimation. So finally, we evaluate performance and fairness using calibrated metrics. And then this slide summarizes the mathematical backbone of our architecture. We use RGCN for relational graph reasoning, GAT for attention-weighted aggregation, and a transformer for temporal encoding across these cycles. So these embeddings are fused and passed into a logic regression or T-learner to estimate conception probability and treatment effects. So we curated 6 distinct datasets capturing demographic, clinical, and physiological dimensions. So after pre-processing and alignment, we merged them into a unified data frame with 17 features. So the EDA revealed stable distributions and minimal missingness, setting a strong foundation for modeling. So this is our feature correlation heat map. And then here we have the exploratory analysis of key categorical variables. That is count and diet type, distribution of diet type, distribution of work type, distribution of estimated day of ovulation, distribution of length of luteal phase, distribution of total days of fertility, and then also gravida. So this is our heterogeneous knowledge graph. These are we combine a temporal transformer for cycle level modeling, then a light GBM for tabular features with monotonic constraints, and a meta model to blend both. So our validation results showed improved calibration and discrimination, but test performance highlights the need for better generalization and fairness checks. So next we have the relational RGCN, TGN, GHC, VGAE, and gene. So we evaluated 4 unsupervised graph embeddings, the ones I have mentioned. So each was trained on the same knowledge graph and paired with logistic regression for conception prediction across all models. The area under curve stayed flat at 0.5, meaning no one could distinguish between positive and negative outcomes. However, the F1 and precision scores were consistently moderate, suggesting that the models learned some structural regularities but lacked discriminative power. So this tells us that unsupervised graph reasoning alone is not enough. So to move forward, we'll need a supervised graph training, richer temporal features, or hybrid integration with mechanistic and clinical signals. So we combined graph embeddings from all the 5 graph models, the ones I mentioned, RGCN, GAT, TGN, VGA, and GENE, into a 160-dimensional representation using late fusion. So the meta classifier performed perfectly on the training set, but generalization collapsed. So our area under curve dropped to 0.42 validation and just it went to 0.6. So this suggests a severe overfitting, while fusion captured structure. Very sorry for that. Fusion captured structure diversity, so it lacked regularization and supervision. So to improve generalization, we are going to explore supervised fusion dimensionality, reduction, or attention-based weighting across embedding sources. So next, we evaluated the model across 4 stages. We have nested cross-validation. It shows a weak but consistent signal. Time-blocked validation, which mimics real-world cycle forecasting, revealed a slight drop in calibration. And then the external validation confirmed limited generalization to new patients. And then the final test performance remained modest with area under curve near 0.50, but a slight gain in precision. So overall, the model is stable but not discriminative. So these points to the need for stronger temporal modeling in the future. So our model shows moderate performance during validation, but fails to generalize to unseen patients in the test set. So this suggests it's learning some signal but overfitting to the training distribution. So when we audit calibration across age and BMI quartiles, we see clear subgroup variation. Older patients are well predicted, while others show distorted probability estimates. So this uneven calibration highlights the need for So as I was saying, it shows older patients are well predicted while others show distorted probability estimates. So this is uneven calibration. It highlights the need for stronger regularization. So next we have the IPW model. It showed a weak ranking, that is a low area under curve and poor calibration, but it maintained a decent F1 score. This suggests that it may be useful in binary decision settings, but require refinement for probabilistic tasks. Then this grounded the sharp comparison. It shows how feature importance shifts across age groups. The progesterone is dominant in younger patients, while psychotiming and BMI take precedence in older cohorts. So, for deployment of the model, we selected late fusion architecture as our primary model. This approach combines multiple predictive signals from graph embeddings, temporal transformers, and mechanistic features. So into this all, we combined it into a unified conception probability estimate. So we tested the 5 graph embedding models. These captured structural relationships from our knowledge graph, but performed poorly in isolation. So late fusion allowed us to integrate their strengths while mitigating individual weaknesses. So we paired this with the transformer head to model cycle-wise temporal dynamics and a T-learner for estimating individualized treatment effects. So this combination enabled us to predict not just whether a conception is likely, but how modifiable factors like stress could improve outcomes. So scientifically, this architecture supports both structural and temporal reasoning. Technically, it is modular, scalable, and compatible with real-time inference and sharp-based interpretability. So our deployment pipeline includes data ingestion, feature engineering, graph construction, model training, and evaluation. So the final model is exposed via an API and a web interface, allowing clinicians or patients to input their cycle data and receive conception probability. So next, I'm going to be demonstrating our product. So I'm going to be demonstrating our product. I'm going to already having a working video. So this is the dashboard. Our product is called Conceive Score. So Conceive Score, this is the dashboard. You track and predict your fertility cycle with smart insights. So this is the dashboard. So you're going to click enter the dashboard. So when you enter the dashboard, there are a lot of, there is the make prediction cycle history. So if it is your first time logging in, you're going to go to the settings and then you put your name, you go to a notification, the account settings, then you can go back to the dashboard if you had already put in those things. So when you look at this cycle, the current cycle, it shows that there is a part for predicting the cycle. So we're going to put the patient index. Patient index is the one that you're given in when you just log onto the app. And then we're going to use the age of 21. And then the BMI, we're going to use 20. Estrogen level, 140. Luteal hormone, we're going to use 2. And then the ovulation trigger hormone, we're going to use 3. Follicle stimulating hormone. Please note that all these hormones are gotten from the hospital. You just don't predict your own hormones. You don't just predict your own level of hormones. So you're going to put in the height, and then the work type, then the diet, and then the cycle number, the number of cycles you've logged in ever since you downloaded the app. The length of your cycle, the days of your menstruation, and then the estimated day of ovulation, and then length of luteal phase, the total days of fertility, and gravida is the number of pregnancies you've had so far. So when you predict with what I have given in, the chances of conception are very high, and it advises you that if the goal is conception, you maintain a healthy lifestyle. If not, you have to use effective birth control methods. So that was our app. So every model obviously has its blind spots. We've identified limitations in graph sparsity, temporal depth, and causal assumptions and data imbalance. There's going to be need for supervised learning, richer lifestyle tracking, and multi-state data sets. The conclusion, we built a graph temporal causal pipeline with late fusion. It achieved interpretability, fairness audits, and subgroup calibration. And in the future, we hope to expand our data sets, improve graph construction, and domain adaptation. So um, these are the references we used that helped us. So we prioritize literature on fairness and explainability to ensure ethical deployment. And then the acknowledgement, we gratefully acknowledge the individuals, institutions, and organizations who have made this research possible. Thank you very much. Please stop.